Okay, everybody, welcome back here. Another quick video. Today we tackle part of nomenclature, and nomenclature is just a fancy way of saying naming things. So in this quick video, we're going to talk about type 1 compounds. So I guess we should start with what are type 1 compounds? Well, type 1 compounds are ionic compounds. And ionic compounds are always a metal and a non-metal together. And whenever you get a metal and a non-metal together, you're going to get this occurring. That metal is going to transfer electrons over to the metal. I'm sorry, the non-metal. So the metal will transfer electrons over to that non-metal. The result of that is the metal's lost electrons becomes a cation, which is positively charged. The non-metal becomes an anion, which is negatively charged. And what holds those things together is electrostatic attraction. Fancy way of saying opposites attract. The positive charge is attracted to the negative charge. There is no sharing of electrons here. So no sharing of electrons, just those two opposite charge guys holding that together. So when we talk about ionic compounds that are made up of ions, it's important to look at our periodic table here. And again, group 1, group 2, group 3. Then we got 4, 5, 6, 7, and 8. Obviously in the middle here, we got our transition metals. So things on the periodic table really do not have charges until they really start combining, for example, metals and non-metals together. But when they do make charges, there are certain elements that have fixed charges. And for the most part, everybody in group 1 is going to form a fixed positive charge of 1. Group 2 is going to be +2. Group 3, and for the most part, it's our friend aluminum here. That's going to be a +3. Right around here on the periodic table where boron is, appears boron. We got kind of that staircase that kind of crawls down and across. And we don't really have a good pattern there in 4. We do go to group 5, and that's going to go -3 and -2 for 6 and -1 for 7. We're really talking above the staircase where we have our non-metals. So it's kind of like +1, +2, +3, skip 4, go backwards, -3, -2, -1. These are positive guys for group 1, 2, and 3 because they're metals. Those are the ones that will lose electrons. And 5, 6, 7, those are negatively charged because those are non-metals that will gain electrons, become more negative. What about the transition metal region? Well, here's our transition metal. And one of the things we're going to talk about perhaps in these videos here about naming is transition metals have the ability to make more than one type of positive charge. So they typically do not have a fixed positive charge. Now, are there some exceptions to that? There are, and they're right about here. Zinc and cadmium, and hang a left-hand turn to silver. These 3 transition metals, even though they are transition metals, they actually do have fixed positive charges. So zinc and cadmium, when they form a charge, will make a +2 charge, and silver will make a +1 charge. Pretty much everybody else out there in the transition metal region, so everybody else in the transition metal region here, and also, by the way, in this area of the periodic table, that's technically not a transition metal, but they also can make a variety of charges. So things like lead and tin and antimony, all these kind of guys in this area, obviously not drawn in the proper spots, but in this area, you'll find these sort of elements, which also have a variable positive charge. So We have ones that have fixed positive charges, groups 1, 2, 3, 5, 6, 7, and zinc, cadmium, and silver. And we have metals, for example, that have variable charges, which are transition metals. So what do we talk about here when we talk about type 2 or type 1? I'm sorry, type 1 ionic compounds. And whenever you're naming, by the way, you always want to look at one of the elements as being maybe more important, and that's our metal and non-metal combination here. And 100% of the time, I would say, if you have a metal involved and you want to name something, that is what you should look at in terms of how you should go about naming. So the metals really quite the most important thing in terms of naming. Now, before we get what type of metal a type 1 is, let's talk just in general about naming cations and anions. So again, cations positively charged, anions negatively charged ions. So when we have cations, for example, type 1 cations, and that's really what makes something a type 1. So maybe I will just talk about what that is real quick here before we get into that. A type 1 metal is one that has a fixed positive charge. So that's what we just saw a second ago on that periodic table. Those are metals that are from group 1, group 2, group 3, zinc, cadmium, or silver. Those are all considered really type 1 metals, fixed positive charges. So when we look at type 1 cations, things like, for example, H plus, Li plus, Ca2 plus, and so forth, we always, when we write the formulas for an ion, they should always include the charges. So the charges should always be written when you write the formula for a cation. How we name positive type 1 cations, we simply just use the whole name of the element, or the metal in most cases. So that's going to be the hydrogen ion at the end. This is lithium, so this would be the lithium ion. This is calcium, which would be the calcium ion. So if you have a positive type 1 metal or cation, we basically just simply use the whole name of the metal, and we put ion at the end if we're writing the form for of an ion. Now, if we have some anions which are negatively charged, say oxygen, which has a -2 charge, Cl -1, chlorine with a -1 charge. Hey, hydrogen is kind of a weird one, even though it's a non-metal. It's kind of treated like a type 1 metal in the sense of naming. And hydrogen is actually one of the few elements that can kind of go both ways. It can be positive or negative. How do we name sort of anions? Well, we use the starting part of the non-metal name. We actually drop the last part and sometimes a little bit more of it, and we end it with IDE. So instead of oxygen here, this would be the oxide, a little bit more than dropping the last part of oxygen, ion. Cl's chlorine becomes the chloride, IDE, ion. And hydrogen becomes the hydride ion. And again, hydrogen is the only one that's kind of like that, can kind of be positive and negative. Most of the time when you see hydrogen, probably going to be positive. It will be negative if it actually comes after a metal. Like, for example, LiH, that is lithium with a +1 charge and hydrogen with a -1 charge. That makes that up. Speaking of formulas for ionic compounds, whenever you take a cation that's positive and put it together with an anion that is negative to make a ionic compound formula, the formula should have no charge. So the formula itself should have no charge, but it is actually made up of two things that do have charges. What do I mean by that? Well, simple example, sodium group 1 plus 1, chloride group 7 minus 1. When I put those together, plus 1 minus 1 equals 0. Just need one of each. So when we write the formula for an ionic compound, it has no charge, but it is actually made up of two ions. It is made up of our cation here, which is sodium, and it's actually made up of our anion here, which is our chloride ion. We always want to put the positive and negative together in the simplest way possible to get no charge. So for example, if I had calcium and bromine, so calcium group number 2, which is why it has a +2 charge, bromine group number 7 on the periodic table, -1 charge. When I put these together, I want it to equal 0. You could probably visually see that you actually need more of the bromide ions in this case. Br minus 1 more, -1 minus 1 gives me a grand total of -2 to balance out the +2 charge that I see on the calcium. And if you actually draw it out like this, when you want to go write the formula, it's pretty simple. You just count how many things you drew. I have 1 calcium, which means I write calcium. I have 1 and 2 of these Br minuses, Br and 2. Remember, the subscript goes to the guy to the left. And if there's just one of something, we don't put 1. There's nothing written. This 2 would go to this Br over here to the left. So the proper formula here would be CaBr2 in this case. Again, it is made up of a cation. That is our calcium with a +2. And by the way, if you needed to write the anion formula, it would be just one of these guys. It would not be, by the way, a very common mistake, that. No, unless you want one of those, probably if whoever's grading your paper, you probably don't want the X. But it actually, that too means that you basically have 1 bromide ion and 2 bromide ions. So again, if you were asked to write the anion for that second one, this is the proper way to do that. Now, I'm a big fan of sort of drawing them out so you can kind of see what's going on. You also can multiply the coefficient or the superscripts together to figure out your common number. So for example, if you had magnesium, which is group number 2, and you put it together with nitrogen, which is group number 5, has a -3. So if you're not sure, you can take 2 and 3 and multiply them together. That's 6, basically. 6 is kind of like your common number in that case. So how many of these Mgs do I need to get to 6? I don't need 1. I don't need 2. But I do need 3 of them to get there. And the nitrides there to get to 6, I actually need 2. +2, +2, and +2 gives me a grand total of +6 that balances out the -3, -3, -6. So again, like I said, if you kind of draw it like this, and if it helps you to do so, you might want to do it. That basically is 1, 2, 3 magnesium. So my formula should be magnesium with a 3, and 1, 2 nitrogens, nitrogen with a 2. Now, I will say that a lot of people are taught to do this, which is take your charges and move them down. And that will get you your subscripts that you need, like so. And the answer is, yeah, that works. And you could also sometimes move them this way to get the charges. And yeah, that works. It does not work 100% of the time, just so you know. Maybe like 94% of the time. So if you're good with 94% of the time, you could just roll with, I'm not really going to think about it and just kind of move things up and down. You will get some wrong along the way, just so you know. Might be better just to kind of think like I've been showing you here, draw out the charges, balance it out, count up how many you have. You'll always get the right answer that way. But if you just randomly sort of do this move, again, 94% of the time, perhaps you'll be right. You will get some wrong for sure along the way. So just keep that in mind. Again, this common sort of way people are taught to sort of do that. So now that we understand how to put it together in the simplest way when we have a type 1 sort of compound, let's talk about actually the naming part of it. So when we have that type 1 ionic compound, as I mentioned before, we have our metal and our non-metal. And once again here, always when a metal is involved, that's what you want to look at. So that type 1, basically, as I said earlier, group 1, group 2, group 3, which is aluminum, zinc, cadmium, or silver. If you see a compound formula that has one of those metals in it, you could just proceed right to the naming part. You don't have to figure out really anything. You just use the whole name of the metal, and our non-metal gets the IDE treatment at the end of it. Again, we dropped the last part of the name. So let's take a look at some of the ones we did a second ago to see how we put this in practice here. We had NaCl. So when I look at this, first thing I want to do is identify what I'm dealing with. So sodium metal, chlorine non-metal. What that first tells me is I'm dealing with an ionic compound. Whenever a metal is involved, as we've been talking about, that is what I want to look at. I look at the metal, that's sodium, that's group 1. Group 1 tells me it's a type 1, which means I'm done looking. All I have to do now is write what is there. So Na is sodium. We're going to use the whole name of it. And chlorine gets the IDE treatment, and we get sodium chloride. Now, if we look at another one that we did, which I think was CaBr2, again, calcium metal, Br bromine non-metal. That automatically tells me ionic. I have a metal involved, which means that is what I want to look at. That is group number 2 on the periodic table. Tells me has a fixed positive charge. Tells me it's type 1. I am now ready to proceed to naming. Whole name of the metal, calcium. And the second guy is bromide, IDE. Now I could hear the question maybe happening right there in your head. Shouldn't it be dibromide? There's like 2 of them, right? And the answer is no, it should not be. So there is no place for prefixes in this type of naming. And people like to do it all the time. Think it looks maybe more chemistry-like or something like that, but you should not do it. So prefixes, there is a specific place where you use them, and this is not the place. How do you know it's not the place? Well, here's a simple rule to follow. If you got a metal, you should not be using a prefix unless you like to get probably a big X. Yeah. So no prefix on the metal. Doesn't matter if you got like 400 of these. Doesn't matter if you got like 300 of the metals. There's no prefix on the first name, no prefix on the second name. In type 1 naming, it is simply whole name of the metal, IDE for non-metal. Why do we have the 2 there is what we saw earlier. Calcium, to balance out that charge, needs not 1, but 1, 2 of these bromide ions. Has no effect on the name though. It is still calcium bromide. Why do we need those 2 to balance it out to 0? Really, the reason is, we're not going to get into this video, but the reason, it actually has to do with bonding. It allows everybody to get to a stable noble gas configuration when you do that and you balance out the charge to 0. One last example here to wrap this up. I think we had Mg3 N2 a second ago. And again here, looking at that, that is a metal magnesium. Nitrogen is a non-metal. Boom, that tells me ionic. I got a metal involved. That's the most important thing. Magnesium's group number 2 tells me it has a fixed positive charge. That is all I need. We're going to go magnesium. And again, nitrogen becomes nitride. So again, no prefixes in this, even though we got multiples here. It has no effect on the name. So that's a really important thing to remember. So now what happens though if we have the name and we want to write the formula? So let's just say we had potassium. Do potassium oxide. And maybe we'll do, how about hydrogen chloride? And one more, maybe. Let's do aluminum. We'll do aluminum sulfide. All right. So let's say we have some names and we want to write the ionic compounds or the formulas here. What should we identify? We should still kind of take the same approach. Potassium is a metal as I cross it out. Oxide is oxygen, which is a non-metal. So I do know it's ionic because of that. And that means I need some ions. So how many ions do I want? Well, I want really just the basic ions to make each of those up. So I know potassium is K, and I know it's group 1, which means it has a positive 1 charge. Oxide is oxygen, which is group number 6 on the periodic table, which means it has a -2 charge. At this point, again, I want to put it together to equal 0 in the simplest way possible. +1, -2, if you're not sure, 2 times 1 is 2. In this case, to get potassium to 2, I need one more of them. That +2, 1 + 1 and +1 will balance out my overall -2 charge over here, giving me the formula of, if you're not sure, 1 and 2 potassiums and 1 oxygen. And gives me my proper formula in that case. Hydrogen chloride. Again, hydrogen really is a non-metal. Chloride's a non-metal. But in the case of naming, hydrogen is sort of treated like a type 1 metal, even though it really is a non-metal. So hydrogen is +1. Chloride is group 7, which means it's -1. In this case, +1 -1 equals 0. I just need one of each to get our formula. Lastly, aluminum, metal. Sulfide is sulfur from the periodic table, non-metal. Again, that tells me ionic. So basic formula for aluminum, group 3 on the periodic table, means it's got a +3. Sulfide, which is sulfur on the periodic table, group 6, means that it has a -2 charge. Again, we want to put this together with no charge. So +3 -2 is 6 if you multiply that together. So 6 is our common number we want to get to. To get our aluminum to 6, we need 3 +3 there. That is 2 of them. And that gives us a total of +6. To get our sulfur to 6, we need not 1, not 2, but 1 more. -2 -2 -2 is -6 in this case. Again, if we just count it up, 1, 2 aluminums. On the bottom, again, going to the guide to the left, 1, 2, 3 sulfurs. And there we go. Perfect formula every time. Well, I was going to wrap up type 1 nomenclature in this quick video. Again, if there's other topics you'd like to hear about, let me know in the comments. I hope this helps you out, and have a good day or night or whenever you're watching this. We'll see you on the next one. Bye-bye.